Hello, let's continue our Sudoku adventure with Thambarskelfir by rockratzero. Loves making me pronounce weird things. All right. Apparently, Thambarskelfir is an old Norse name. It's the nickname of Einar Thambarskelfir, a notable Norwegian nobleman and archer during the late Viking Age. So, archery related. That's why we have our arrows. All right. Well, let's go over the rules. We do have normal 6x6 Sudoku rules. So we're placing the digits 1 to 6 in each row, column, and 2x3 box, once each. So these arrows in the grid. So the arrows are attached to a circle. Digits on an arrow sum to the value in the circle. There's no non-repeat clause added on, tacked on. So we just have to follow Sudoku rules. So we could make this 1, 1, 1, 1, and that would add to 4, for example. All right. Additionally, we have a single between line here. So we have a line, and then we have two circles, one at each end. And the digits on the line have to be strictly in between the digits in the circles. So if this was 2 and 5, then all of these digits would need to be from 3, 4 only. It cannot be outside of the 2, 5 range and can't be 2 or 5 themselves. So 3 and 4 would be the only options. All right, if that's 2, 5. And that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. All right, how shall we get started? We do have a given 6 in this arrow, but it is not hard to make this add to 6. So if we want to think about degrees of freedom here, the minimum this could be is a 1, and the minimum this could be is a 1, 2 pair. So that adds to 4, meaning we have 2 degrees of freedom. So all of these could be up to 2 higher, and we'd still be able to reach the sum. So in fact, we need in some way to add 2 to this sum, right? So we could go to up to 2 or 3 here. We could go 3, 4 here or 3, 4 here, but this one's not a 3. Now, something I'm wondering about, because these are near each other, is whether we can combine these arrows together. So I'm gonna actually remove this pencil mark here. What we can do is we can think about the smallest all of green could add to. And that is going to be the smallest that these 3 circles could add to. So I usually use a greedy algorithm here. It usually works out where you don't want to pick a row, column, or box that takes the most cells as possible. So for example, we can take this box and get that this has to be from 1, 2, 3. We can take this box and this has to be from 1, 2, 3. This has to be 1, 2 pair for this box and 1 for this. You can mix rows and columns also. Like we could have made this having to be 1, 2, 3, and then this would be 1, 2, but it doesn't actually make a difference. We have. I don't think we can do any better. You want to group as many greens as possible into each group as you go, but I don't think we can beat 3, 3, 2, 1. So anyway, 1, 2, 3 adds to 6. So this would be 6, 12, 15, 16. So 16 is the smallest this could add to. Now, what's the largest this could add to? Well, we know this is already 6. And so the largest this could add to is a 5, 6 pair here, which is a total of 17. So we have 1 degree of freedom here. This always needs a 6 in it, and it's either 4, 6 or 5, 6, and then we can add 1 to any of these digits. So we can add a 2 to here, a 3 to here, a 4 to here, and a 4 to here. Now, of course, we can clean up these 3s now. So this is slightly better than what we had here, but you can see we have additional restrictions on these that we wouldn't have known earlier. Okay, I don't think I need the green cells anymore. We can remove those. Now, we have 1, 2, 4 triple here. So this is where 5, 6 go. This 6 is not here, though. So that's 5, that's 6. That does place the 6 here. So this definitely adds to 6. Its minimum is 4. So we have 2 degrees of freedom. So this can't actually be a 4. Right, if we try to make a 4 here, we'd have to add 3 more to it, and that would add to 7. So that's not a 4, and this is not a 4. Okay. We know there's a 4. Okay, we know there's a 4, actually. So that uses up one of our degrees of freedom. And so it has to add to 11. Because this isn't 1, 2, 3, 1, 2, 3, 1, 2, 1, because we know there's a 4 involved in one of these two just by Sudoku. And so that actually does mean that we can't put another 4 anywhere. And it also means this has to be a 5. Very nice. Okay. Glad I spotted that. Now here's another little trick. Between lines can't ever have a 1 on them, because what are you going to put outside of the 1 in the circle? A 0? No. All right, so no 1s or 6s on these cells. And so where does 6 go in this box? It goes here. I mean, I guess we already knew that. And 6 in this box goes here. So neither end of this is 6. I think we have to have a 5, do we? Well, this could be a 1. Oh, we can't have another degree of freedom. This has to be a 1-2 pair. Right. If you think about it, we know this is 1, 2, 4. That adds to 7. And then this adds to 6. We can group this differently, right? This adds to 7 plus 6, which is, sorry, that's 13. Plus another 3 is 16. This is 17. And 17 is what we made this add to. Yeah, that's the biggest it could have gotten. So this actually has to be a 1. And so now neither of these are 1 or 6. So 2, 5, I think is required here, right? We can't put a 2 on here anymore because the lowest that these can get is 2. So that forces the 3 and the 4, and that does mean this is a 2, 5 pair. So that's our 2, that's our 5. Okay. This is working. This is really nice, Rockrat. I'm actually really enjoying this. This is a 5, and this is a 4, and this is a 1. All right, we know these are just filled with 3s and 4s. So that's our 3. All right. In fact, my example ended up being the correct range. That was not intentional. I didn't know what it was going to be. That's a 3. We have 2 and 4 here. The 1-2 pair tells us that this is the 4 and this is the 2, making this guy a 3. All right. These 1-2 pairs will work out and just make our sums correct, I think. You know what? How are we going to get to 6 here? We need 2 2s and 2 1s. And this needs to add to 3. This is a 1-2 pair. Unfortunately, this 1-2 pair sees that cell and that cell, so that's not helpful. We have 1-2 pair, 1-2 pair. Oh, so we know this digit. This is a 4. And then this is a... Oh, we need a 3, which goes here, and we need a 5. All right, this is a 1-2 pair. Interesting. The arrows are going to have to resolve something. We need a 4 here, and we need a 6 here. Over here, we need a 5, and then here we need a 4. Okay, so we got to figure out how this is resolving. I'm going to color the 1-2 pairs. So we got green, purple, green, purple. I'm coloring them by how they see each other. So we know these two are the same digit. If they were 1s, then that would add to 3, and we would not be able to get to 6 because we would need another 3 here. So these have to be the 2s, and this is the 1, and that makes that 2, 1, and 1. We don't need these colors. Over here we get the 2 and the 1, and we're done. Correct solution. Very nice. Let's just double check. 1, 2, 3 is 6. 1, 2, 2, 1 is 6, and 1, 4 is 5. All right. Again, very cool puzzle, Rockrat. I really liked the flow on that one, and it had some really neat deductions. I like being able to combine the arrows, and then we kept using that during our solve to be like, oh, I found the degree of freedom, so we can't use the degree of freedom anywhere else. I was a little bit slow on the uptake there, but I mean, who is perfect? Certainly not me. All right, cool. Well, let me know how you did. If you enjoyed it, why not leave a like, subscribe, and a kind comment below.